Hi, in this video we're going to discuss implicit differentiation. This is a type of differentiation that you need to use when your variables are not easily separable. For example, in almost all of our examples, we've been able to solve for y or f of x explicitly in terms of x. Here are some examples of functions where you can solve explicitly for y. There are some relationships or functions that involve x and y that are not easily solved for y. For example, if you look at these here, you can see it would not be very easy to separate out the y's in terms of x. In these last examples, we're going to say that y is a function of x, and we're going to treat it like a black box. In other words, what we're going to be doing is we're going to be using the chain rule whenever we see a y, and we're going to assume that it's a function of x that we can't isolate. We are going to use the differential notation dy dx to solve for the derivative because it's a lot easier to understand that we're finding the derivative of y with respect to x if we use this notation. Here's an example. Suppose I want to find dy dx, so in other words, the derivative of y with respect to x, if the relationship between x and y is given by this equation. So what we're going to do is differentiate both sides of the equation with respect to x, and every time we come across a y, we're going to use the chain rule. We're going to differentiate the outer function, which is the y that we see, and then we're going to multiply that by the derivative of the interior function that we can't see. In other words, we're going to just multiply by dy dx. Here's an example of how to differentiate implicitly. Suppose we have a variable term 2y, and we want to differentiate it. The 2, of course, is the 2y is our function. We're going to basically say the derivative of the outer function y is 2 times 1, okay, and the derivative of the inner function is dy dx. And they're multiplied together because we're using the chain rule. Now, when you see y and x multiplied together, you need to treat it like a product because y is a function of x. Okay, you're going to use the chain rule on that. And of course, you're going to differentiate x as one of the factors in the product. Let's take a look at our implicit function above. We have the first term is 3xy. We're going to treat that as the product of 3x and y, and we're going to use the product rule on it. So our first function in the product, u, is going to be 3x. Its derivative is 3. The second function in the product is y, and since y is a function of x, we need to use the chain rule on it. The derivative of y, the outer function, is 1, and the derivative of the interior function that we can't solve for is dy dx, the derivative of y with respect to x. Then we just use the product rule to plug in the pieces. U times v prime plus v times u prime. We're going to rewrite it so it's algebraically consistent, and we're going to plug that in. Here's the second term. We have 4y squared. Okay, and we know that y is a function of x, so we differentiate the outside that we can see, the 4y squared. That's going to be 2 times 4 is 8. Drop the exponent on the y, 8y. But again, because y is a function of x, we need to differentiate the interior function y that we can't see, and that's where we get the dy dx. The entire derivative, then, is the 3x dy dx plus 3y, that's from the product rule, and this is the derivative of the 4y squared term. Of course, the 10 on the other side gave us a derivative of 0 because it's a constant. The rest of the problem is just algebra. Now all we have to do is isolate dy dx. The way to do that is to keep the terms with dy dx on one side of the equation and move any terms, such as this 3y, that don't have a dy dx in them over to the other side. So here is that 3y being subtracted from both sides, and it shows up on the right-hand side with a negative sign. Since all the terms on the left now have a dy dx as a factor, we're going to factor that out. The last step is, since this dy dx is multiplying the quantity in parentheses, we're going to divide both sides by the quantity in parentheses to isolate dy dx. And there is your implicitly differentiated y prime. If you want to see the steps listed out, we have them here. Okay? First, differentiate both sides of the equation with respect to x. And again, the thing to keep in mind is y is a function of x, and every time you see it, you're going to need to use the chain rule on it. The other two steps are algebraic. You're going to place all the terms with a dy dx on one side of the equation, and you do that by subtracting or adding any terms that don't have dy dx from both sides. Last step, factor out dy dx from all the terms that contain it, and then divide by whatever the quantity is in parentheses to isolate dy dx. Let's look at some more examples. Here, we want to find dy dx, and you can see this would also be a difficult equation to solve for y, so we're going to differentiate implicitly. Before we do that, though, we're going to rewrite this to express the square root term with exponents. The reason why we do that is it's much easier to use the product rule for differentiation when you have exponents. So here we have x plus x to the 1/2, y to the 1/2 equals y squared. And again, we notice since x and y are multiplied in this term here, we need to use the product rule on it. Okay, so over here I kind of have a product rule laid out for this term. Okay, u of x is x to the 1/2, v of x is y to the 1/2. If you differentiate both of these, remember, bring down the 1/2, subtract 1 from the exponent, bring down the 1/2, subtract 1 from the exponent. But over here, since y is a function of x, again, I have the chain rule. Here's the derivative of the outer function, and dy dx is the derivative of the inner function. All right, so here I'm plugging in what I got for the product. Again, I have u times v prime plus v times u prime. Here's the derivative of the first term x, that's just a 1. And on the right-hand side of the equation, I have the derivative of y squared. Differentiate the outside function to get 2y, and the derivative of the inside function, the y I can't solve for, that's dy dx. Now I get to isolate all the dy dx terms on one side. Okay, so here I have, I've done some moving around. For example, from this term, I took the 1/2 and I put it out front because that's just conventionally the way we write algebraic terms with the coefficients out front. So this term has become 1/2, x to the 1/2, y to the negative 1/2, dy dx. The only other term with dy dx was from the right-hand side of the equation, so I'm going to subtract that. It'll wind up on the left-hand side with a negative sign. And then any term without dy dx, which are these two, wind up over here with negative signs in front because they've been subtracted. Again, I brought the 1/2 out in front here, so I have negative 1/2, y to the 1/2, x to the negative 1/2. That's this term right here. And then I've subtracted this 1 over here. Last thing to do is to factor out dy dx. And again, I'm putting all of the terms that contain it. Okay, once I've divided out dy dx, they're in parentheses. Last step, divide by the quantity in parentheses. Now this is pretty much a mess, and it can be simplified further by rewriting things and factoring things out. Again, my goal here is to just show you the calculus step and how to isolate dy dx. The algebra I'll leave up to you. Here's an application example. For example, in what situation would you want to use implicit differentiation? Let's take a look at a demand function. Okay, we have a demand function for a certain commodity. You'll remember that in a demand function, P represents the price, in this case in dollars, and Q is the demand for the product, and we're told down here demand is in hundreds of units. We want to find the rate of change of demand with respect to price when demand is 100 units. Now it's important to read this carefully. We want to find the rate of change of demand. The demand variable is Q, and rate of change is telling us take the derivative of Q with respect to P. Okay, it's very important to get this the right way round. You don't want to do it in, backwards. So we're looking for dq dp, and then we want to evaluate it when Q is 100. Okay, so if you take a look, you'll notice there are no variables in the numerator of the demand function, so it'd be really easy to rewrite this a little bit algebraically by taking the quantity in the denominator, putting it in parentheses, and giving it a -1 as an exponent. You do not need to use the quotient rule on this because we don't technically have a quotient of variables. We've only got the variable in the denominator. Again, since I'm differentiating of Q with respect to P, okay, let me take a look over here. dq dp. P is like X and Q is like Y. So that means I'm going to treat P like the variable X. And whenever I see a Q, I'm going to use the chain rule on it. Okay, so here's implicit differentiation on both sides. Remember, P is like X, so if I'm differentiating it with respect to itself, I get a 1. This coefficient just gets pulled through the differentiation process. Just pull it through. Again, it's not a constant in the sense that it's a standalone term. It's multiplying the rest of this expression. So just pull it through. Then we have this big expression. You can see it's a composite function. Okay, the interior function is this cubic, and then it's raised to a power. So I'm going to need to use the chain rule on it. Bring down the -1, rewrite the interior function, drop the exponent by 1, then take the derivative of the inside. Now some of these are Q's, right? They're Q variables. So since Q is a function of P, every time I differentiate a Q, I'm going to use the chain rule a second time. Here's the derivative of that first term outside function. So 2Q to the third differentiates to 6Q squared. And here's the derivative of the interior function Q that I'm not solving for. Okay. Here's the second term. It also has a Q in it. The derivative of the outside function 400Q is 400. The derivative of the interior function Q is dq dp. And of course the 5,000 gives us a 0. All of this on the right hand side is multiplied together. The next step is to isolate dq dp. Okay, so what I've done here, since in this set of parentheses dq dp is in both terms, I've just factored it out right here. Then notice all of these factors are multiplied together. The -500,000, okay, and again I multiplied the -1 and brought the negative sign out front. This term in parentheses raised to the -2nd, and then this term in parentheses. They're not terms, they're actually factors, okay? So basically these three factors are all multiplied together. So I can just divide by that product of factors to isolate dq dp. They're going to divide out on the right side, and then they're all going to divide the 1 on the left side. Okay, and again, this negative sign's coming out over here. Okay, so here is my final expression for dq dp. Again, you don't need to overly simplify it algebraically. It just needs to be neat enough for you to be able to plug in 100 for q. Again, do this on your calculator. Please, if you're using a TI-84, use the alpha y equals numerator denominator. Okay, so you're making sure that everything is where you expect it to be. Okay, and everywhere you see a q, you can either put the value 100 in parentheses, or you can just multiply by 100. So that'll be here, here, and here. Once I did that on my TI-84, like this, I got about negative 138. Now it's important, because this was an applied problem, to interpret your answer with units. Since we found dq dp, and dq is in hundreds of units produced, and p is in dollars, the units on your rate are 100 units per dollar. Okay, so basically what I'm saying over here, when we plugged in 100 for demand, but that was 100 units. So when demand was 10,000 units, demand is decreasing at a rate of 13,800 units per dollar change in price. That means every time the price goes up $1, you wind up with your demand decreasing by 13,800 units. Again, 13,800 is just this number, 138, multiplied by 100, because that's the units of our demand. And again, the negative sign tells you that your demand is decreasing.